Okay, week two. So we're gonna be doing chapter two or this week's chapter two stuff in two parts. We got a bunch of things on the menu here. This video is just gonna be 2.1 and 2.2, logical operators and translation, and syntax of propositional logic, well-formed formulas, and main operators. All right. So starting off, logical operators and translation. Um, so, as sort of obvious, propositional logic is logic that uses propositions and inferential relations between propositions. Propositions are statements that have a truth value. So, a lot of the time we can think about these as just being sentences. Propositional logic is sometimes called sentential logic. But having a truth value is the sort of major important feature. Um, So you can think of the difference between a statement like, say, a statement, but I could say an ungrammatical sentence just like if I said apples are, that as an incomplete sentence, it can't have a truth value by itself. I could say apples. I could point to an apple if there's an apple somewhere. I could say apple to try to get you to realize that I'm referring to this object and I'm calling it an apple and maybe there is one or something like that. But as far as what I'm saying, the truth value of just a statement like apples or saying apples are, it can't have a truth value. It can't be true or false. But if I say apples are red, now this is a complete sentence that can have a truth value. It can be true that apples are red. It could be false that apples are red. Um, and in the logical system that or the logic that we'll be using for this course is only two possible truth values, true and false. Other logics can have more than two values. For example, some logics will have true, false, and indeterminate or undetermined, or and then other logical systems will have many more than just true or false for truth values. But we don't have to worry about that in this class. True and false are the only possible truth values for propositions to have. So, yeah, all the above examples of propositions. Propositions are just going to be statements that can be true or false. So work in propositional logic begins by specifying a formal object language. So for the purposes of this course, we're calling it PL, which stands for propositional uh, logic. So in propositional logic, we'll represent simple sentences with an uppercase letter. Uppercase is important here. Um, in the latter half of the course, well, when we're going to be working in monadic predicate logic, we'll be using lowercase letters that'll have a specific meaning that's going to be different from uppercase letters. That's a different logical language, so you don't have to worry too much about mixing it up, but it is important that capital letters in this case represent simple sentences. So in the previous example I gave, if I say apples are red, I can just use the capital letter A to stand for apples are red, and that's um, just using that variable to stand in for the simple sentence will allow us to regiment arguments in a way that reveals their structure completely, gets us away from any of the content, etc., etc. So an example here, the sentence, it is snowing, can be represented with a simple S. So in the argument, anywhere that I want to say it is snowing, I can just have an S instead. Right. And so if we have simple sentences that are represented by um, just a uppercase letter in English, that's our variable that we're working with, we can use operators to modify the meanings or to express a relation between two of these other variables um, using these tools that we'll talk about here. So we start with a simple sentence like it is snowing or apples are red or something like that. That can be, we can use just a standard uppercase letter to indicate that, but we can build out more complicated sentences using operators. So we're going to be using 5 operators here in propositional logic. So the first is the tilde, the dot, the vel, the horseshoe, and the triple bar. And these will all have meanings that we'll discuss. And part of the reason why I'm having you handwrite your homework assignments rather than do them in a word processor or something like that is because we're going to be using symbols like, so the tilde standardly on keyboards, but dots and vels importantly are not V's. You'll notice here it's sort of more centered than a V is. It's a different symbol than a V. Horseshoes and triple bars are just kind of non-standard symbols that we could either come up with an equivalent to use that are on keyboards or some other way to actually get these symbols in a word processor like I've done here, but I think it's just easier to handwrite these. And there's other symbols that will come up further down the line that it will just make it easier to handwrite. There's other formatting issues, like once we get into doing proofs and we could have a nested proofs indenting these in a certain way, it's just easier to do by hand. So these non-standard symbols are a large reason why I'm having you handwrite homework and exams and stuff like that. So we'll get into the meaning of what each of these operators show. So the tilde represents negation. This should be pretty intuitive. Sort of, you're going to be negating something. So negation, for example, if S stands for it is snowing, then tilde S would stand for it is not snowing, or it is not the case that it is snowing. It sounds a little awkward in English, but standardly the best way to sort of sound out when you're reading these formulas and proofs and stuff that have all these symbols in them, it is good practice to just put them in ordinary English for yourself as you're working through it. And for the tilde, it is not the case that is just going to be, that's going to work in the most amount of cases, even though it sounds sort of awkward. But it reveals something more obvious about the logical structure. It would also be okay just to say not S here. But if we try to think about what S means, if we say not it is not, or if we say not it is snowing, that doesn't work quite as well. But if we say it is not the case that S, and then if S means it is snowing, then this would mean it is not the case that it is snowing. This ends up just sort of working out better. Anyway, so a tilde is going to mean that it is not the case that something, whatever follows the tilde. So negation is unique in that it is a unary operator. It applies to one propositional variable. It doesn't connect propositions together. All of the other operators that we have are going to connect different propositions in different ways, but the negation just applies to one thing. I can have S for it is snowing, and I can have not S, which means it is not the case that it is snowing. So a couple of things on this point. So this was something that was brought up in the text, but in the reading for this week, but it bears reiteration. So and this mostly matters when we'll be doing regimentation, and we'll sort of quickly move out of this, but it's important to keep in mind, and I think it's a good point to make. So you should be careful when assigning negations in predicate logic, because negations in predicate logic have a kind of specific meaning. The example that was given in the text is these two sentences here, where the first one is Kant affirms that arithmetic is synthetic a priori, and the second one, Kant denies that arithmetic is synthetic a priori. Now these seem like the opposite of each other, and if it is true that Kant affirms that arithmetic is synthetic a priori, then it is true, or then it is not the case that Kant denies that arithmetic is synthetic a priori. But if it is not the case that Kant denies that arithmetic is synthetic a priori, that doesn't necessarily mean that he affirms it. So we wouldn't want to express the second sentence as being just the negation of the first. Now, the reason for this is that these two sentences are what we call contrary rather than contradictory. Now, contrary sentences can't be true at the same time. It can't be, both of these sentences can't be true. They're um, contrary to one another. But contradictory sentences are different because if you have a pair of contradictory sentences and you negate one of them, that means that the other one must be true. So, for example, if I have two sentences, houses are red, and it is not the case that houses are red. Well, if I negate houses are red, then I get the sentence, it is not the case that houses are red. Fair enough. If I negate the second sentence, if I say it is not the case that it is not the case that houses are red, then what that means is that houses are red. Like that, it means that the other sentence must be true. There's no middle term that we can appeal to. Whereas in the example with Kant affirming or denying that arithmetic is synthetic a priori, and if you're interested, he does affirm that arithmetic is synthetic a priori. This is sort of a big deal for him, but it's not relevant to our purposes. Like the book says, it's possible that someone could neither affirm nor deny that arithmetic is synthetic a priori. They could just remain silent on it. So if I negate that Kant denies, if I say it is not the case that Kant denies that arithmetic is synthetic a priori, there's a couple possibilities. One, he could affirm it. Two, he could just say nothing about it. He might not be interested in denying it. And so for that reason, we would want to, when regimenting either of these sentences, we would want to make them both sort of positive, even though in the one case, Kant denying that arithmetic is synthetic a priori seems like a negation of the other sentence. It would really be cleaner to regiment it as just uppercase English letter on its own. So the difference between contraries and contradictories isn't going to come up a whole lot, but it is important for our purposes that if I have a simple sentence, let's say A, and I have not A, then these are the only two possibilities. This is what will be called in informal logic classes the law of the excluded middle, where if you have something and its opposite, there's no other possibility. I could say either houses are red or it is not the case that houses are red. There's no option that doesn't fall into one of these two terms. And if there's no possibility for any option that doesn't fall under one of these two categories, then if I know that it is not one of these two categories, then it must be the other one. This will be important later on when we're working with doing proofs, and we'll run into situations where you'll have a statement that says, well, if we know it's true that P or Q, and we know that not Q, well, then we know that it must be P. Well, that's maybe not exactly a clear example of what I'm trying to talk about here. We'll get into that at a later point. But for our purposes, negation should be understood in this way, where a sentence and its negation should be understood as being the only two possibilities. There can't be a third term. And if there could be a third term, then we would have to think about regimenting it in a different way. All right. So moving on to conjunction. So the dot represents a conjunction. In some other, if you are looking for other resources online, this might be represented in other ways, but for the purposes of this class and the assignments that you do in this class, please use this notation. So the dot just means and, or but, or just something to combine two terms at once. So the example here is if S stands for it is snowing and C stands for it is snow, then S and C stands for it is snowing and it is cold. S is true and C is true. Now, conjunctions, well, other than the negation, the negation. Here, let me go back to this. Actually, this is worth talking about. So when I have not s, we'll get into this more when we talk about truth tables and so on. The thing that I am most interested in is what the value of the negation is in this case. Now, if I know the value of s, then I know what the value of the negation is going to be. Because if s is true, then not s is going to be false. And if s is false, then not s is going to be true. Um, and so we'll talk about this more in the future. But when there's an operator on a variable, the operator is a sort of higher level instance of a truth value that we care about. Now we can get to that truth value if we know what the variable's truth values are. We can determine what the truth value of the operators themselves are going to be, but something to keep in mind. Conjunctions are going to be true when both sides of the conjunction is true. And conjunctions, like every other operator other than the negation, are binary. They're going to be connecting two elements together. So we can call either half of a conjunction S and C. The S, when it's inside, or when it's connected to the C with the dot here, will be one of the conjuncts of this conjunction. And you can read this when you're just looking at it as S and C. All right, disjunction. Conjunction and disjunction sound very similar. They're importantly different. Here we'll use the vel to represent a disjunction. So disjunction is going to be, instead of and, we're using or. So if S stands for it is snowing and R stands for it is raining, then if I say S or R, it means it is snowing or it is raining. So again, this is going to be connecting two terms. One of the points in the book that bears reiteration is that the disjunction that we'll be using for the purposes of this course is inclusive. It's possible for a disjunction to be true when both S and R, if we're using this example, when both S and R are true. Disjunction is also going to be true when just S is true or when just R is true. So if the statement that I'm concerned about the truth value of is it is snowing or it is raining, and it is true that it is snowing, but it is false that it is raining, then it is true that it is snowing or it is raining. Because when I say it is snowing or it is raining, I'm just interested in it being one of these two things. It doesn't matter which one. In this case, it can even be both because we're using an inclusive or. But as long as one of the two sides, at least, is true, then the statement that one or the other of them is true is itself going to be true. And a disjunction is going to be false when neither side of it is true. If it is not snowing and it is not raining, then it is not the case that it is snowing or raining. We'll get back to this later on. You may have noticed that I expressed the negation of this disjunction in terms of a conjunction. We'll get to that when we talk about logical equivalence. Just flagging it for you a little bit. Don't worry about it too much yet. But one of the powerful things about these languages and being able to look at just the sort of strict form of the content that we're working with is we'll find that you can express things in a lot of different ways. Different sentences or different formulas will be logically equivalent to one another when we wouldn't maybe ordinarily think of phrasing something in that way in English, but that'll allow us to see connections or get to conclusions that otherwise aren't as intuitive. So that's one of the benefits of symbolic logic. All right, next. So this is the trickiest one. I'm flagging it for you right here because this is something to pay attention to and some people are going to struggle with. And this is probably the one that's worth investing the most amount of time into just really making sure you understand what's going on. So material implication, we're going to use the horseshoe, this little sideways U-shaped thing. So the horseshoe represents material implication or the conditional. material implication translates to if-then statements. So, for example, if S stands for it is snowing and C stands for it is cold, then if S then C stands for if it is cold, then it is snowing. So material implication is also a binary operator. Unlike all of our other binary operators, the conjunction and the disjunction, and we'll have one other that we talk about after this. So I'll go back to this here, actually. So I have S or R here. R or S instead of S or R would be completely equivalent. The order of the S and the R here doesn't matter at all. However, with material implication, the order is extremely important. If S then C is completely different from if C then S. So we'll talk about this a little more. So the first part of the conditional is called the antecedent. If I say, if it rains, then the earth will get wet, then if it rains is the antecedent, and then what comes after then is called the consequent. So the first part of the conditional is the antecedent, and the second part is called the consequent. This should be fairly easy to remember. Consequent sounds like consequence. It's sort of what happens as a result of something else. So that can be helpful for remembering which part of the conditional statement is called what. We have the antecedent and the consequent. Antecedent also ante, before, etc. So that can be helpful for remembering which side is called which, but I wouldn't lean too heavily on the temporal elements of these two terms in understanding what is logically implied by one of these statements. So I'll explain what I mean. So the antecedent is what we call a sufficient condition of the consequent, and the consequent is the necessary condition of the antecedent. I'll explain what that means. But first of all, it seems a little bit weird to think about the consequent as a condition of anything that comes first, the antecedent, if we're thinking about it in temporal terms. Now, we shouldn't do this. Because that'll make things a little bit tricky. If you translate the temporal meanings of consequent and antecedent, etc., into what's logically implied in a conditional. So I'll talk a little bit about sufficient and necessary conditions here. A sufficient condition means that, let's say, if there's some condition that has to be met, or it's a condition that if it's met, implies automatically something else. Whereas a necessary condition is a condition that must be met in order for something else to happen, but isn't necessarily sufficient on its own. I'll give you an example. Having 4 sides is a necessary condition for a square. For an object to be a square, it must have 4 sides. However, having 4 sides is not a sufficient condition for being a square. Something could have 4 sides and not be a square because the sides are unequal lengths. For example, we could have a rectangle or some other kind of polygon. So if I refine my statement to say something like, well, if something has 4 equal sides and 4 90-degree angles, then it's a square. In that case, there's sort of multiple elements that are being brought together in order to achieve the sufficient conditions for a square. Now, something could have infinitely many, maybe not infinitely many, because then it would be difficult to get to any sufficient condition. But let's say something has 1,000 necessary conditions. And if it has 1,000 necessary conditions, then they all have to be present in order for it to be sufficient, let's say. So the sufficient condition guarantees that something comes after it. A necessary condition doesn't guarantee something in the same way, except if you already have that thing. So, for example, if I have an object that is a square, well, then I know certainly it has four sides. Four sides is a necessary condition of being a square. It's just not a sufficient condition. There's more to being a square than having four sides. So, let's talk about this in terms of conditionals. Um, so if I say something like, if an object is a square, then it has four sides. In this case, being a square is a sufficient condition for having four sides, and having four sides is a necessary condition of being a square. Easy enough. If we reverse them, it doesn't work. Where I say, if an object has four sides, then it is a square. Now, obviously, there's other kinds of objects that have four sides, so I don't know certainly that if an object has four sides, that it is a square. So this is an example of why you can't just reverse the sides of a conditional statement, that they're very important to keep in mind, which side's which. So the four sides example is a situation in which a condition can be necessary but not sufficient. But it's also possible for conditions to be sufficient without being necessary. So for example, I can say that being red is a sufficient condition of being a primary color. If something is red, then it is a primary color. However, being a primary color, red is not a necessary condition for being a primary color, because I could meet the conditions for being a primary color without any red whatsoever. For example, I could have yellow instead. So even though I can say if something is red, then it is a primary color, I can't say if something is a primary color, then it is red. It could be a different primary color. So any of the examples of primary colors are not necessary conditions for being a primary color, but each of them is sufficient for being a primary color. A sufficient condition just guarantees that if the condition is there, then you have something else that follows it. And if there is a sufficient condition relationship, then whatever the consequent is, in that case, we can say is a necessary condition of the thing that you started with. Now, this gets a little weird to think about if we take something that isn't sort of immediately present in the way that primary colors and redness or four-sidedness and squares are related. There isn't any kind of temporal gap there in what's happening. But if I take a statement like, if it rains, then the earth will get wet, it's sort of weird to think about the earth getting wet as a necessary condition of it raining. Because when we think like, well, that doesn't, like the earth wouldn't need to get wet in order for it to rain. So don't think about it in that way. What we're concerned here is just the relationship between raining and the earth getting wet. And if it is true that if it rains, then the earth will get wet, then anytime there is raining, there must be the earth being wet at the same time. And if the earth must be wet at any time that the earth, or at any time that it is raining, because we're assuming that it is true that if it rains, then the earth will get wet. And so since raining is a sufficient condition for the earth being wet, then the earth will always be wet in any instance where it is raining. So because it is always there alongside raining, we can say that if this relationship is true, that if it rains, the earth gets wet, then the earth getting wet is a necessary condition of it raining. Even though it doesn't seem like the earth being wet is required in any ordinary way for it to rain, it is a necessary condition as far as this logical relation between these two statements holds. So that's something to keep in mind also, is that when we're working with translating or regimenting arguments or phrases in different ways. Don't get too hung up on sufficient and necessary conditions having any kind of temporal element to them, or situations in which it doesn't really make sense that you would need one thing for the other thing, but just think about the logical relation between the two things in the statement that is given. If it is true that if it rains, the earth gets wet, then any instance of it raining entails the earth being wet. So if the earth is always wet whenever it rains, then we can say that these two things are necessarily connected. The earth being wet then is a necessary condition of the antecedent, it raining. So even though the term is necessary condition, don't let that make you think that it is something that has to be met in order for the other thing to happen in the first place. It's just, in this case, something that always comes along with it. That may be a little unclear, but we'll be going over this a lot, hopefully, the next 3 or 4 times that I explain it, because I'll probably explain this a few times. It'll sink in if it didn't already. All right. So when translating conditionals, whatever comes after the if is the antecedent, whatever comes after the only if is the consequent. So this gets back to what I was just explaining. So we can think about material implication as with the antecedent and the consequent in a couple of ways. The simplest way is just if something, then something else. Only if has a different meaning here. So when we're talking about, for example, if you have primary colors, I can't say that if something is, so I can say if something is red, then it is a primary color. I can't say only if something is red, then it is a primary color, because there's other ways in which it could be a primary color. So let's look at these two examples. So the first is you will pass if you study. So we can regiment this if we say that studying stands for S, you study is S, and you will pass is P. So if I know that you will pass if you study, I could say if you will pass, then you will study. So if S, then P. However, in the second sentence, it says you will pass only if you study. So in the first sentence, you will pass if you study. This guarantees that if you study, then you will pass, but it doesn't specify that studying is the only possible way to pass. It guarantees that you'll pass, but you might pass otherwise. The second sentence is saying you will pass only if you study. In this situation, it is impossible for you to pass in any other situations. So we know if it's impossible to pass except for studying, then we know that if you passed, then you studied. Whereas in the first case, we don't know that, because it's possible that, while we know that it's guaranteed that you will pass if you studied, it's possible that you could have passed otherwise. So I can't say if you passed, then you studied, because maybe you were just lucky or something like that. But in the second sentence, it says you will pass only if you study. This yields a different kind of conditional statement, where the only thing that we are certain of is that if you passed, because the only condition for passing was studying, then that means that, well, if you passed, then you studied. I can go from one thing to the other because I know that passing automatically entails studying in this case. All right. This again we'll talk about some more. The second, or not second, this last operation here deals with ifs and only ifs as well. So the triple bar represents what we call the biconditional. The biconditional translates to if and only if. There's some other terms that the book gives, but if and only if is the most common one. So if S stands for it is snowing and C stands for it is cold, then C, if and only if S stands for it is cold, if and only if it is snowing. The biconditional is a binary operator like all of them except for the negation. So the biconditional, this makes sense if you think about the different ways that you can get to conditional statements using if statements and only if statements. Because it's using both if and only if, well, it makes sense that we could express this as a conjunction of two different conditional statements. I can say if A then B, and if B then A, or A only if B. So if I want to have a biconditional, which is just going to be, in this case, A if and only if B, this means that I have both of these conditional statements together. If A then B, and if B then A. So you don't have to worry about this too much, but it'll be helpful further down the line when we're doing rules of equivalence. If A if and only if B is logically equivalent to if A then B and if B then A. So here, instead of just one side being the necessary condition and the other side being the sufficient condition, both sides are necessary and sufficient conditions of the other. This is a sort of very strong connection that they have here. So let's do some examples. So if A stands for you study and P stands for you pass, how would you read the following? In the first instance, we've got S vel P, and so we'd read that as just S or P, which means either you studied or you passed, which doesn't make a whole lot of sense by itself, but logically that's not a problem. We're just concerned with one of these two statements being true, either S or P. So you studied or you passed. Here we have a conjunction instead of a disjunction where we're using the dot rather than the vel. So this would be S and P, or you study and you pass. You study and you pass. So here we have slightly more complex. We've got not S and not P. So this would translate to it is not the case that you study and it is not the case that you pass. This by itself, well, never mind. I'd be getting ahead of myself there. All right, next we've got if S, then P. So if you study, then you will pass. Next, it is not the case that S, that if it is not the case that S, then it is not the case that P. So it is not if it is not the case that you study, then it is not the case that you pass. And here, S if and only if P. So you study if and only if you pass. And here we have S or not P, or you study, or it is not the case that you pass. So with these, it's sort of helpful to read them out in this way sometimes, instead of just looking at it as S horseshoe P or something like that. Thinking about it as if S then P will be sort of more helpful for being able to read these sort of strings of symbols and letters in a way that makes it a little bit more coherent for you. And that it'll help you, I think, grasp and understand the logical structure of what you're working with a little bit more. If in situations where you have an actual content, in this case, like you study and you pass, it can be helpful to consider the content in terms of like what the logical operations are, but it can also be, it can make things more confusing, especially when you get into ifs and only ifs, um, and things being necessary or sufficient conditions. Those can be a little bit unintuitive if you try to think about them in terms of their content constantly. Um, so that's one thing to be aware of. Okay. All right. So next we'll move on to the content from 2.2. Syntax of propositional logic, well-formed formulas, and main operators. So the language of propositional logic can be specified more precisely in terms of formal syntax and semantics. So this is like the vocabulary and rules for making formulas. So here's the what we'll call the vocabulary of propositional logic. Um, so so the basic unit that we're going to be working with is uppercase letters. This will be the simplest, most fundamental unit that we'll be concerned with. Then we'll have the operators that will modify those. And we'll have these punctuation marks. So the book, I changed this here. The book has you use parentheses and brackets and braces. Um, I think it's actually just sort of cleaner to use parentheses all the way through. Um, that it'll be a little bit easier to see. I'll show you some stuff when we're working through that on the board, but don't worry about using brackets or braces, but you will have to use sort of nested parentheticals. Um, we'll talk about that more later. But I don't care if you use brackets or braces. It's sort of easiest for me to read if you just stick to parentheses and kind of keep things clean. Um, but so these are the um, pieces that we'll be using for propositional logic. All right. So the next thing is going to be the formation rules for proposition logic. This will be in order to build what we call well-formed formulas. So a well-formed formula is any logical symbol or string of symbols that is constructed properly. Um, so a well-formed formula is going to be analogous to a grammatically correct sentence. So it's analogous to a grammatically correct sentence. So, like for example, I can't say apples are, uh, something's missing there. I can say apples are good. I can't say good apples are. If I mix things up, then the meaning gets lost and it doesn't make any sense. Um, so it's important for us to be able to recognize what is a well-formed formula and how to identify the different pieces of a well-formed formula. There'll be a couple of questions on the exam, probably about where I'll give you some examples and you'll be asked to identify whether or not it is in fact a well-formed formula. So we'll talk about the formation rules next. So the first rule is a single capital English letter is a well-formed formula. And remember, a single capital English letter stands for a simple sentence. Something like, apples are good. A. That is going to be by itself, with nothing else going on. We have a well-formed formula there. So the single letter, apples are good, the A for apples are good, that's going to be a well-formed formula. The second rule of, so this first, this should be PL1, not PLT. When I was working on this, I did a find and replace for ones and zeros for true and false. We'll get to that later. Anyway, this should be PL1. Let me change that real quick, actually. Okay, I fixed that. So there might be a couple of weird things that come up, but I'll talk about that more when we get to truth tables later. So the first formation rule is a single capital English letter is a well-formed formula. PL2, if alpha is a well-formed formula, then so is not alpha. So this is something that they talk about a little bit in the textbook, but I'll say here, the use of the Greek letters, alpha, just stands for any well-formed formula. Now, well-formed formulas can be just a single capital English letter, like it says, but they can also be very complex. So when we're looking at these formation rules, if it says if alpha is a well-formed formula, then so is not alpha. So if I have a very complex formula, and I take that entire formula and negate it, then it's a well-formed formula. Now, if I have a very simple formula, let's say P, and I negate it, well, because P by itself is a well-formed formula, then the negation of P is a well-formed formula. But the reason it's using alpha here is just to stand in for any well-formed formula that can be very complex, it could be very simple, but if you have a well-formed formula, and then you negate the entire thing, then it is, again, just a well-formed formula. All right, so if alpha is a well-formed formula, so is not alpha. PL3, if alpha and beta are well-formed formulas, so of alpha and beta can be well-formed formulas of any complexity, then so are alpha and beta, alpha or beta, alpha then beta, if alpha then beta, and alpha if and only if beta. So these are all different ways that well-formed formulas can be combined, and they are still well-formed formulas. So first with a negation, then with conjunction, disjunction, conditional, and biconditional. All right. So these are the only ways to make well-formed formulas. Now, so for example, if I take, let's say if I have if P and Q, then S. And I take that entire thing and I negate it, and I say, that's by itself is going to be a well-formed formula. And I say it is not the case that if P and Q then S, that's also going to be a well-formed formula. If P and Q then S would stand in for alpha in PL2, for example. Alpha and beta, again, just different well-formed formulas. This I think can get confusing sometimes, but the rules for well-formed formulas, the Greek letters again stand for any well-formed formula, which can be just a single capital English letter, or it can be any infinitely more complex version than that. So long as only these rules were used in constructing it, then it is always a well-formed formula. All right. So next, an atomic formula is formed by a single use of, again, this should be PL1. I'll go ahead and fix that. Okay, that should be fixed. An atomic formula is formed by a single use of PL1. If we remember, PL1 is just a single capital English letter, well-formed formula. So any single capital English letter is going to be an atomic formula. A complex formula is one formed in any other way. So if we have a single capital English letter that by itself is atomic, that's the smallest unit of well-formed formula that we can have. Anything else going to be that's added to that is going to be complex. Even if it's just, let's say P is our atomic formula. If we have not P, then it's a complex formula because we have the atomic part P, but there's more operators that are going on and being added to that. If we have P and Q, different example of a complex formula. So S is an atomic formula, so A, B, C, X, Y, Z. Not S is a complex formula, so is if not S, then P. So main operators are what we would say is the last part of the formula to get created. So formulas that get very complex, it's extremely important. This is where parentheses come in. It's extremely important that we kind of keep them in order, what order they were created in. And the main operator is going to be the last thing that was added to a formula, and it's what characterizes the formula overall. So, for example, if we have the formula, we would read this as if S or P, then Q and R. This is when we talk about what kind of formula this is. It is a conditional formula because the conditional is the last piece that was added to it. So you can see we have these parentheses around S or P, and we have parentheses around Q and R. Now, if we connected all of these open parentheses to each other, one easy way to determine what the major operator is it'll be, because we leave out, and the book talks about this a little bit, we'll leave out the outermost parentheses. If we connect all of the open parentheses to each other, whatever's left outside of parentheticals is going to be the major operator. So if we connect these two here, we know that this is just a part of one side of this conditional. If we connect these two here, then they're enclosed, and then the conditional itself is going to be left outside of that. So the main operator, or the major operator, is what characterizes the entire formula. Now, if you have, let's say if you have P, and then you have not P, the major operator of not P is going to be the negation. Negation works a little bit differently with the parentheticals. If it's just connected to a variable by itself, but if you have not P, then the negation is going to be the major operator. We would characterize the formula not P as a negation. All right, so we'll do some practice here. So in this case, we have the formula not S or P if and only if Q and R. So again, if we do what I talked about in the first instance, where we sort of connect all of the open parentheticals, you'll see that the biconditional is going to be left out of the parentheticals at the end of it. So the biconditional right here is going to be the major operator. We would characterize this formula as a biconditional, even though it has a negation and a disjunction and a conjunction inside of it. So if SP, Q, and R are all well-formed formulas by PL1, again, there we go. I gotta be more careful with the find and replace. So SP, Q, and R are all well-formed formulas by PL1. They're just uppercase English letters that stand for some simple sentence. So then, not S is a well-formed formula by PL2. That's sort of the next part that we can get to in order to determine, let's say, the truth value of the conditional, because the conditional here is comparing the value of not S to P. If we know the value of S, then we need to know the value of not S. Then we can compare that to P. Then we can get to the value of the conditional. So we build up from the smallest parts to the biggest ones, first with pretty much in the order of the PL rules, where we start with just the value of the variables, then the values of the negations, except in cases where the negations are on the outside, but here it's all the same level, and then the values of the other parts, and so on. So if S, P, Q, and R are all well-formed formulas, then not S is a well-formed formula. So if not S or P and Q and R, so if not S is a well-formed formula, then not S or P is a well-formed formula, because alpha or beta is a well-formed formula, and Q and R are well-formed formulas by PL3, then the whole formula is a well-formed formula by PL3. Because we can take the left side of the biconditional, not S or P, we know that's a well-formed formula, so we can just call it alpha. And the right side of the biconditional, Q and R, we can just call beta because Q and R is a well-formed formula. Then what we have here is alpha if and only if beta, and we know that's a well-formed formula. So the whole thing is then going to be a well-formed formula. All right. So let's do some examples. Are the following formulas well-formed formulas? If so, what is the main operator? So in the first case, we have not S or P. This one's a little bit tricky. So the main operator here is the vel. This is going to be a disjunction. One of the disjuncts is not S, the other disjunct is P. So it is a well-formed formula, and the vel is the main operator. However, if there were parentheses around the S and around the P, and the tilde was outside of the parentheses, then the tilde would be the major operator. Right now this reads not S or P, but if the tilde was on the outside and the parentheses were closing off S or P, then it would read, it is not the case that S or P. It's just a difference in how they're moved around. But if there's no parentheses after the tilde, then the tilde is just going to be modifying the variable that's right next to it. So this is a well-formed formula. The vel is the major operator that makes this a disjunction. So here's the example I was just talking about, actually. So here we have, it is not the case that S or P. S is a well-formed formula. It's just a capital English letter. P is a well-formed formula. Capital English letter as well. We know that S or P is a capital English letter. We know that S or P is a well-formed formula because it's just a disjunction between two capital English letters. So that's a well-formed formula. And we know that the negation of a well-formed formula, in this case, the well-formed formula is S or P, is itself a well-formed formula. So this instance is also a well-formed formula, and the major operator is the negation. So this is a negation. All right. Next we have a couple of things. S, R, and P are all going to be well-formed formulas. S and R is a well-formed formula because it's just a conjunction of two well-formed formulas. It is not the case that S and R, this itself is going to be a well-formed formula because it follows exactly the same structure as above it here. It is not the case that S or P. Not P is a well-formed formula. However, there's nothing connecting the not S and R and the not P. Things are just sort of floating out there. So this there's yeah, they're not connected to each other in any way. So because they're given here as just one formula, this is not a well-formed formula. It doesn't make any sense. It's unreadable in the same way that an ungrammatical sentence would be. Ungrammatical sentences in English are a little bit more flexible because we can interpret the meanings in different ways. Here we have no flexibility whatsoever. This formula doesn't mean anything. It is not a well-formed formula. There's no major operator. All right. So here we have several parentheticals. So the innermost one is if Q then T, and if Q then T, then Z, and if Q then T, then Z, then P. So we can, if we closed off the Q and T here, and then closed off the next parentheses, which was the q, if q then t is the antecedent to a conditional where the consequent is z. If we closed that off, then we would see that this conditional falls outside of the other parentheticals. So we know that this conditional here is the major operator. Now, if we didn't have these parentheses that showed us which condition was the major operator, that would change the meaning of what we have going on completely. So because we have the parentheses that show us that this, while Q, T, Z, and P are each by themselves atomic formulas, the next formula that we go to is, well, if Q and T are well-formed formulas, then if Q then T is a well-formed formula. So we know that. Then, if that's a well-formed formula, then if Q then T then Z, then this is a well-formed formula. And then we do the same thing again for P here. We know that if it is true that Q then T, then it is true that Z, and if that is true, then P. So this is a little tricky to talk about because it's a lot of conditionals in a row, but the major operator is going to be this conditional on the P here. Okay. Now you see in this case, it's unclear where to start from. We start with the Q and the T and the Z. Those are well-formed formulas, but immediately things go awry. The only way to make a well-formed formula is a connection between one well-formed formula and another well-formed formula with an operator, a conditional in this case. But here we have three well-formed formulas and two operators between them. And we don't know what order it is. Is it if Q then T then Z, or if Q then T then Z? The logical meaning of these sentences would be completely different depending on whether we had parentheses here around the if Q then T, or between around the T if T then Z. So in the first, if we had parentheses around T and Z, for example, then my antecedent is just Q. And my consequent is if T then Z, which is different from if I had parentheses around if Q then T, which would make if Q then T the antecedent by itself, and the consequent would be Z. I would be saying if this relationship between Q and T is true, then Z is certainly true. Whereas in the other case, I'd be saying if Q is true, then this relationship between T and Z is true. So this is not a well-formed formula. There's no major operator. There's nothing we can do with this one. All right. This one is going to be a little bit more complex. So first thing to do here is look at all our parentheticals. So we've got this parenthetical that connects these two. Great. We've got this parenthetical that connects these two. Good. This parenthetical that connects S or P. Great. And then we've got this parenthetical which connects all of this stuff here, which the major operator in this parenthetical is a biconditional. Then we have a negation of everything in here. Then on this side we have a conditional, and then SNR. Okay, a lot of stuff going on here. So if we connected all of these parentheticals, there would be two operators that fall outside of them. One would be this conditional here, and the other would be this negation. However, this negation is applying to this biconditional. So the negation, so conventionally, we don't use parentheses in quite the same way that we do with negations as with everything else. So this negation is just applying to the antecedent. So the major operator of the antecedent, if we connected all of the open parentheses on the antecedent of the conditional, the major operator would be this negation. Now, if there were another pair of parentheses that opened here and closed on the opposite side here, then the major operator of this entire thing would be a negation. As it is, the major operator is the conditional, this horseshoe. So let's start from the parts. S, P, Q, and R, and SR again, we're using the same variable a couple of times. Capital English letters on their own, well-formed formulas. Start with the consequent here because it's simple. The consequent of this negation is just S and R. So conjunction of two well-formed formulas is itself a well-formed formula. This side's all good. All right. Inside here, so first we've got S or P. S or P is a well-formed formula. Then we've got Q and R. Q and R is a well-formed formula. So if either of these sides of the biconditional are well-formed formulas, then the biconditional that connects the two well-formed formulas is itself a well-formed formula. So S or P, if and only if Q and R is a well-formed formula. And if that's a well-formed formula, what's inside these parentheses here, then the negation of that is going to be a well-formed formula. So we have two well-formed formulas on either side of this conditional. And if the conditional is connecting two well-formed formulas together, then the entire thing is a well-formed formula. So this is a well-formed formula, and the conditional is the main operator. All right, how about this one? So we'll look at it the same way, where you can see that the only difference here is that there was an extra parentheses that connected everything together except the negation. So I sort of forgot that I had this in here. I already spoiled it a little bit, but the difference is going to be that the major operator in this case is going to be the negation. Because instead of just this side of the conditional, it's including the entire formula within it. It's negating the entire formula. So this is going to negate the horseshoe, and so the value is going to be completely different. But again, the one way to determine this is if we close all of these parentheses, then in this case, the negation is the only thing left outside of the parentheses. In the previous case, there were two things outside of it, but we could see that the negation in this case applied to this entire side of the antecedent. So the value of the negation is what we're going to be comparing. The value of the negation is the antecedent, and then we have the consequent on the other side. In this case, the entire formula is just the negation. So the negation isn't applying to the biconditional, it's applying to the conditional here. So this is a well-formed formula. The major operator is the negation. All right. So semantics of PL, this I'll get into in the next video. This is long enough for the first one. For 2.3, 2.4, that'll be the next video. Yeah, see you then.